Hello there. Welcome back. This time I'm not going to start off with the lightsaber. Well, okay, I do have a lightsaber, but we're going to dive right in with really this gets at a very simple example of a machine learning algorithm. And I'll go ahead and show in Excel a few different ways that this can work. And so hopefully you follow along with this simple example, which kind of sets us right up to where we kick off the course and talk about linear regression, logistic regression, and a number of different machine learning concepts that continue to pop up. So without further ado, okay, this is the second part of this video. For the machine learning for everybody, and again, this is the second part of the machine learning primer. Here we're just going to talk about Control L basics. Matrix multiplication. mmult is the Excel function for that. Optimization. Talk a little bit about x's and y's and y hat and what those terms mean. These are going to be variables that we repeatedly bring up as we talk about kind of the math involved with these machine learning algorithms. So first, the definition, what is artificial intelligence or AI? Again, artificial intelligence, it's performing functions and tasks that normally require human intelligence, especially learning, which is gaining knowledge, reasoning, using that knowledge to solve problems. Sometimes these are categorized in very different ways. Some people might even throw superhuman AI and other things in there. Here I just say, hey, there's narrow AI, maybe limited or broad AI, general AI, and it involves, like, do you train it to perform like a very narrow or limited scope? You can do that. You can do broad AI, creating an AI that's going to perform multiple tasks. Maybe transfer some of the knowledge from one task over to another. And then general AI, or as you start getting into human level AI, it's going to I'm saying it thinks. It's going to the mathematics of it are going to allow it to do more generalized tasks, even tasks that it hasn't been trained on, but it can map the knowledge that these algorithms contain within it in order to demonstrate human-like behaviors and adapting to new tasks for a wide range of cognitive ability. Machine learning is kind of a subset of AI. So AI can function without machine learning, but machine learning is becoming more the common practice of how these artificial intelligence algorithms operate. What machine learning does, it allows computers to learn directly from examples, data, and experience without being explicitly programmed. So there is expert systems was a popular term in the past that described humans that were trying to embed their knowledge within kind of a decision tree almost of how they go about like solving a task. In machine learning, you're gathering the data and the experience and allowing these algorithms to be trained on that. So you have these mathematical models or algorithms that are going to use this training data in order to optimize the model parameters. And in that way, you're going to allow them to take input out in an operational setting and provide output predictions for a particular task. So, when you think of machine learning, think of an algorithm that is trained on the data that we give it. In general, here's an analogy. AI is more the flashy sports car. and will contain really all the complex systems built around the machine learning algorithm, which I show here as the engine. I mean, machine learning algorithms are really what's powering this and what differentiates, how good your AI is. But it's not entirely everything, right? Artificial intelligence is going to have a lot of scaffolding built around it in order to make it work. Whereas machine learning is kind of a subset of that. It's a very important part of that AI architecture, but it's not everything. So why now? Why are people learning about machine learning and AI now? And we can go left to right here, but there's a number of reasons, and I've just chosen 4 of them that seem to play a big role in why we're learning about machine learning. One would be chip technology. Through Moore's law, computing power has increased, over the last 5-6 decades. I mean, and continues to increase. So as we go along, there's more and more computing power. And specifically, they're adapting to these algorithms now to make them even more powerful. The second is big data. There's more and more massive data sets these days. In fact, the amount of data accumulated in just a year these days is incredible. So these massive data sets are giving a lot of information for these machine learning algorithms to learn from, to train with. The third one, internet and cloud computing. Certainly the open source coding libraries and frameworks, the ability to share these algorithms openly on platforms like GitHub has led to almost accelerating progress in training new models. And then the last one, the algorithms. Certainly, because of this internet, cloud computing, open source libraries, frameworks, it's led to improved machine learning algorithms as we go along. So certainly machine learning AI is here to stay and is a big part of why these AI algorithms are performing so well. So you may be asking yourself, do you really need to understand it? And I know there's been some, what I would say, opinions out there that you don't need to understand advanced mathematics or computer programming languages to, be able to go out and kind of understand how AI maps onto your organization's needs. I tend to not like that perspective as much. I tend to look at this like I really want to understand what's going on under the hood, so I know kind of the limits of how much we can trust machine learning and AI, what sort of applications within our organization is it going to be good for, where is it not going to be good for. And then we're increasingly being asked to evaluate and integrate this into technologies, concepts, partnerships. I think we need to know a lot about it in order to answer those questions. So at a minimum, what is the state of the art right now? What's beyond the state of the art? Really understanding where machine learning is right now, I think is important in order for how you can apply that. And what we're going to really cover here, when you look at this whole machine learning, artificial intelligence, this top sort of row is really showing kind of in an operational context, like how it's being applied. But what we're going to cover is really this bottom row. which is the training data. We have inputs and outputs, which I'll refer to as X and Y. X being inputs, Y being outputs. It goes into these machine learning training algorithms. F is the function. So we have a function, and then theta, commonly used to refer to as model parameters. So we have the model, and then we have the model parameters. And all that's going to train a model that then goes into software that then can be deployed in an operational setting. So when you hear the terms like AI ops, machine ML ops, or machine learning ops, they're really talking about this top part. How do you then take these algorithms and build a system around it? In order for them to really tackle kind of the operational issues that you may be having in your organization. Knew it was a black box, but we're going to really unpack that black box so that you can understand what's going on inside it. So, there's a number of different ways that you can sort of break apart machine learning, and here's a few of them. So this is one way to kind of break them up and think about the different types of machine learning. Supervised learning. So in supervised learning, you're going to have inputs and you're going to have outputs or labels. So whenever you have inputs and outputs, you're going to be using something like supervised learning. Unsupervised learning, cover a little bit in this course as we get into things like autoencoders. It uses data but doesn't require labels for the data. So you can kind of see off to the side here, I have labels for supervised, no labels for unsupervised. Semi-supervised will have some labels. So in some situations, you have a little bit of labeled data, so inputs and outputs, and a lot of unlabeled data. And so there's smart ways that you can use algorithms that can take both of those and come up with a better prediction than just approaching it with a supervised algorithm or an unsupervised algorithm. And then reinforcement learning is something a lot of times tied with autonomous AI agents or robotics. It's more a learn as we go sort of process. So there's a different flavor of machine learning algorithms for reinforcement learning, a different approach. Not going to cover that as much in this course, but just understand that there's these other approaches that are out there that are also helpful in certain applications. Okay, so here's our examples. On the left-hand side is supervised machine learning. On the right is unsupervised. So recall that supervised has inputs and outputs, so it has labels, if you will. So in this example, you see 6 different images of cats and dogs in Star Wars outfits. And below it, it's labeled cat or dog. So cat, dog, dog, cat, dog. And what your supervised machine learning algorithm is going to be trained to do then is to predict, when given a new image, is it a dog or is it a cat? Unsupervised machine learning, we have all the images, but there's no label. So there's no output response. So, here you don't have labels. You're going to train this machine learning algorithm. And that machine learning algorithm is going to know that when there's a new image, it looks an awful lot like this cluster that I have over here. So you can see it kind of separated dogs and cats into different categories. Doesn't know that they're dogs or cats, just simply that there's similar features within, in this case, these images, that it says, okay, these all look similar and these also look similar. And when given a new image, it can also kind of separate that into the different categories. And then, as I mentioned, semi-supervised is going to take, sometimes a little bit of labeled data and a lot of unlabeled data, and integrate it into an algorithm that's going to get really good at predicting dog or cat. So much better than if you just trained a supervised algorithm on, the labeled data. So what is supervised machine learning? Here's where we get into some of the vocabulary, the definitions, how I'm going to present the math. I'll go ahead and turn my laser pointer back on. So we have this data set here. And the inputs we're going to call X. So these are going to be, it could be features or attributes or factors. In the case of images, X is going to be the image itself, which has multiple pixels with values in it. This is going to get fed into an algorithm along with outputs. So, your outputs I'll describe as Y, or you could think of these as responses as well. And what the machine learning algorithm is composed of is, you see F and theta. So F is the actual function. So, this would be your real physical model in the world. F hat, I don't use this term a lot, but just know that the hat means an approximation. So there's an actual function in the world that nobody knows about that describes the relationship between inputs and outputs. And what we're actually doing is we're going to approximate that with an algorithm. And so when you actually look at the equation, what you have is the response, can be predicted by a function that includes the inputs, and it also includes the model parameters, theta. So here we go. What we have is a data set is equal to inputs and the outputs. And then the machine learning algorithm is going to learn the relationship between those inputs and between those outputs. And in the process of learning the relationship, it's going to train these model parameters. Such that, at some future point, if you want to make a prediction with a new input, you can insert the new input, X, to make a prediction of the response. So Y hat, again, being an approximation or prediction of a new output or new response. Okay, so now on to our example. And here you go. This is just kind of goofy, and there's a backstory here. You can pause the video if you want to read all this. But essentially, we're going to try to program this very simple algorithm, to be able to predict whether something is a cat or a dog. Okay, so, if you want, you can load up this outside of here. I think I'll put the link, or may have shared this Excel file with you, but that's not necessary. I'm going to actually run through the different examples and how it works within Excel. Okay. So let's imagine that our data set consists of these four examples. And we have X1, X2, and X3. So what these are is we have three different inputs for each of these examples. One might be the color. So the color we can call X1. And that's a value that runs from 0 to 1. So 1 being black, 0 being white, maybe values in between being something that's different than black or white. Tail length could be the second input or feature. And so I just made up some tail lengths here. Weight can be x3. That can be the third input. And so, we might have different weights of these different examples. So, this might be x1, x2, and x3 and how it would look in a spreadsheet-like format. And so what unsupervised machine learning might do is might start to look at, relationships between the inputs. So it starts to look at weight and tail length and notice that, this might be a cluster and this might be a cluster, which just so happen to coincide with cats and dogs. But these algorithms don't know that term. They're just looking at the relationships between the inputs. Now, if you want to add and tackle this with a supervised machine learning algorithm, you're going to need a response or a label. So this is your Y, your response. And what this response is it a cat? So this is a binary, a yes or no answer. So yes, this is a cat. Yes, this is a cat. So we're going to put those as 1. No, this is not a cat. No, this is not a cat. These are both dogs. So those would be a 0. So now we have our Y, put into this table as well. And so this is the actual, response or actual label. We haven't made the model yet to predict that. And in this simple example, we can use just a straight line, whereas theta might be, the slope term that acts on each of the different features. And I'll show you what that equation looks like in just a little bit. So here you can see x3, the weight, so the weight is very high for the dogs, it's very low for the cats. So you would predict that this theta might actually be, a good way to distinguish between what's a cat and what is a dog. So that's going to act on this third input. So just to get you familiar with some of the ways I present this in terms of a mathematical function, once again up here, Y is a function of both the input and the model parameters. And if we want to go back to a very simple example, we could make this function where we have theta 1, so a slope-like term acting on x1, and then we can add a bias term or an intercept term, so that doesn't act on any of the different inputs. So it's more like a baseline value there. And now if we want to do this for 3 different inputs, we're going to have a slope term or a model parameter that's acting on, and when I say acting on, I mean multiplied by each of these inputs, x1, x2, x3, and we're still going to have this theta naught term, which is really an intercept term, a baseline term. Okay, now if we go back to linear algebra, I'll just show you kind of how this works. Is we have this function here, and so here's just 1, 2, 3, 4, and we're going to multiply that matrix by another matrix of variables a, b, c, and d. And this is going to give us 1 times a, 2 times b, 3 times c, 4 times d. And then this function is going to be the summation of all of those. Now what's really nice is if we add another row to this matrix, we're going to get another value, which is 5 times A, 6 times B, 7 times C, 8 times D. So now we're going to be returned with 2 output responses, 1 for each of the rows in this first matrix. And computers are really good at doing these operations. They're very fast. So I use that example because, now what you actually have here is you have x1, x2, and x3. So you could put those values in this first matrix. And what the second matrix is theta naught, theta 1, theta 2, theta 3. These are your model parameters. So this first one is an example of one observation. So you look at one of these, one observation or one test, and when you multiply these matrices together, you're going to get one prediction. Now, you can have a lot of different observations, though. So this matrix would be an example of multiple observations or multiple tests, if you will. And then you can have multiple different inputs. So here we just show 3, but there's no reason why this can't be 10 or 100 or 1,000. So this matrix can expand. The interesting part is these model parameters don't need to expand with it. So in this example, we're only going to have 4 model parameters, no matter how many different observations or tests that we have in this first matrix. And it's going to give us a prediction for each of these rows. So this is the basis, this matrix multiplication, of many of the machine learning algorithms that I'll be discussing, and is really at the center of these neural networks as well. So if you recall, there's another video out here that I show one of these examples. So in this case, if you'll recall, or maybe you're going to view this afterwards, there were 1,000 different observations. You can see x1 through x10, so there's 10 different features. I just used random numbers for all of these, and then you have theta 1 through theta 10. So each of those is going to act on the input features, as well as theta naught, which is going to act on this x naught column, which we've set to 1. So in that way, when you multiply theta naught by 1, it's going to be theta naught. And we showed how you can very easily, with one formula, fill in all of these 1,000 predictions in Excel. And this setup within Excel is the exact same as what you have up here. So instead of 1, 2, and 3, here we have 11 different model parameters. And instead of this matrix, we're going to have the matrix that spans from x naught all the way to x10 and goes down these 1,000 rows. And then the function xy is going to be your output y. So this is going to be your prediction of the response. And then if you really look at this, this simple example has all the elements of a machine learning algorithm. And so I'll go ahead and kind of show the terminology that we'll be using and learning about through this course. So first there's a model. The model is a function or an algorithm, that often has model parameters and inputs. So these thetas, these are your model parameters. Initialization, you have to initialize them originally. You can't just leave them blank. So you're going to have to put some values in, like make a first guess. You then turn that over to optimization later, and that optimization process is going to be what will find the best model parameters for the data, the training data that you gave the algorithm. Here are all your inputs. Here is your output. Here, again, I termed it y hat. This is going to be your prediction. So this is your actual response from your data set, and this is going to be your predicted response based on this model up above. This column that says loss, This is going to be evaluating how good your prediction is. So there's a mathematical way to compare your actual responses with your predictions. And so, this is going to be used in the optimization process in order to update the model parameters. Now, when you're doing optimization, though, it's usually easiest to operate on one value. So you're going to drive one value either as low or as high as it can go, given the constraints and given your model parameters. So this is called a cost function, and this is going to be like a total evaluation of the model. And then you have some test sets down below, which are applying the model to new inputs in order to make a prediction. So these are all the terms of machine learning. And after you set this up, then you're going to go ahead and optimize it. Okay, at this point, I thought I'd shift over to Excel to show you actually how, like, 3 different methods for solving this simple machine learning algorithm, if you will. It's a linear regression algorithm within Excel and what that looks like. So I'll go ahead and pull up Excel. So there we go. Okay, so this is just as we showed in the different slides that we just covered. I'll go over here. The first thing we want to do is initialize our model parameters or our theta values. So I'm going to zeros in all of those. The prediction, this is where we're going to use that matrix multiplication algorithm. Remember x comma theta. And because we haven't named them, it's just outlining the cells as we do this. So enter. And again, because it's a dynamic array, it's going to encompass all 4 of these values. Now we're going to do the loss function for each of these. And in order to do that, we're going to do, this will be y minus y hat. You notice that it put the hashtag because it realizes that's a dynamic array. And we're going to square that. And it's going to, each of these is going to correspond to the same row. So these first 2 are a loss of 1 or a high loss because the actual value of 1 is different than the prediction, which is 0. We are then going to do the cost function, and this is simply the average of the different loss functions. There we go. 0.5 is what it comes up to. Now at this point, we can do the optimization. So to find the actual optimized model parameters, or these different theta values up above in this equation. So we want to go to the data tab. Again, solver is this optimization tool. Set the objective, so we can actually go here. We can select the cost function as what we're going to optimize. We're going to force that to be a minimum. And we want to do that by changing different cells, so we can select the different theta cells. These arrows off to the side are just showing that like theta 3 acts on this column, theta 2 acts on this column, theta 1 acts on this column, just to kind of highlight which of these model parameters acts on which column. So now we can go back here. We are not going to enter any constraints. We're just going to use this nonlinear solver, so kind of the default within Excel, and go ahead and solve. So it takes a couple seconds. So I'll pull this over here so you can actually see what I see. It found a solution, and you have the option to keep the solution or restore the original values. We're going to keep the solution, okay. And you see up at the top here, that it now has optimized these such that the prediction 1, 1, 0, 0 is equal to the actual values. Okay, so that is one way to do this. And then the next thing, if you wanted to predict new values, you would do the matrix multiplication of the new x's with your theta parameters. I'm going to put F4 here just so that doesn't move. Okay, there's one prediction, and now I can Control C to copy, and I can paste it down below too. Control V to paste, and if we wanted to look at, now it's highlighting the correct cells, these new ones off to the left, and it's still using these model parameters. Okay, so that's one way to do it. That's kind of the quick and dirty way to do these problems. If I want to, I can go ahead and delete this. I can go ahead and delete these, 0. You know, the other way that we can do this is we can actually go and assign variable names. So we can select all these. Again, go into that upper corner and just name it X. Let's name all of these theta. We can actually select all of these and use, I believe it's in formulas, create from selection. And here we can create variables, and you're just telling it the top row is going to be the variable names. Select OK. So now it's named each of these columns according to the top row. And then the last one would be the cost function. So we can, let's name it cost. Enter. Okay, so the prediction, it's still going to be matrix multiplication, but now we can just enter the names. X comma theta, the mean squared is going to be equal y minus y hat squared. And the cost is going to be equal to the average of loss. And again, each time we're doing this, you can see that loss is blue, and it's outlined the correct array up above. You know, press enter, and there's our cost function. I should have probably left the values, but we can do solver again. When you open solver this time, notice that it's replaced the actual cell with the variable name. So it's going to set the cost function to a minimum by changing the theta variable cells. And we'll go ahead and push solve. Once again, it's solve this, press OK, and there we go. And then the last way is to use what's called a let function, which I've outlined before, you know, but we'll go ahead and do it again here. It's going to take, we're going to use actual multiple different lines. So this is why I've expanded that, you know, formula bar up above. So we're going to use the let function. And in the let function, we're going to identify x, and we're going to select this. We're going to identify theta, and we're going to select our theta up above. We're going to identify y. We're going to select y. And you notice it's replacing the cell names with the variable name that we've already... So it may be confusing, you know, but the second set of values, the first one's always going to be the variable, or the odd one within this function. And the second is going to be where you highlight the different cells that are going to make up that variable. Okay, so those are all really our inputs that we need. I can hit Alt-Enter and go to the second line. Now we're going to, well, we would have to calculate y hat. So y hat is going to be matrix multiplication of x comma theta. We're going to have to do the loss. The loss is y minus y hat squared, and then the cost is the average of the loss. And then I'm going to hit Alt-Enter again. The very last value is going to be the value that you output. Since we're in this cost cell, I'm going to output the cost. So press Enter. And there we've done everything within one in-cell formula. What's interesting is we don't have to have y hat and loss in order for this formula to work. And that's because it can calculate intermediate cells within this formula. So that makes it really nice if you have a lot of intermediate steps that you would like to tackle, not on the spreadsheet, but maybe within within a cell or a formula, and you really only want the output. So that's where this function comes in very handy. So with that, these are kind of the three ways that you can approach this problem. Again, maybe I'll show you even the solver here. In this case, again, the cost function and theta are referencing these different cells. Even though we've deleted y hat and loss, we can still run the solver. Of course, we already had it set to the correct values, but even if they're not, this solver would work without those intermediate values. The other interesting thing is if, maybe you needed to debug and you were curious what these intermediate values were, you could go back and say, okay, I'm going to take y hat and I want to output y hat. So there we go there. Well, that's the y hat value. I'm going to go ahead and copy this formula once again. I'm going to go over to the loss function and paste it. And I want to know what the loss functions are. So you can paste those intermediate values if you want to try to debug or to see if the formulas are working, which is sometimes necessary. But the let function will do all that internally without you requiring to do those intermediate steps. The other thing I could show with this loss function is we don't need to define the cost function up here. I could go ahead and just cut that out, and I'm going to go ahead and delete, and I'm just going to output the average of loss at the end. So you can do something like that where the output value actually uses a formula as well. If I press enter, it still gives us that 0 value. So we didn't need to identify a new variable in order to make that calculation, but sometimes it's nice just to keep track of what all is going on. So with that, yes, thank you, and for hanging in there, and hopefully this helps to show you a few ways that you can tackle these sort of problems within Excel. And with that, we're going to move on to really understanding the basics of machine learning, and then from there to tackling the basics of neural networks. So with that, that's it for this video, and may the course be with you.